So hello everyone, myself Venu, lecturer in mechanical engineering from Government Polytechnic Varangal. So since we have seen the video lessons regarding the previous topics, if you observe, regarding we have seen the vapor absorption refrigeration system, and the continuation we will see the practical. Last video lesson, it is an ideal vapor absorption refrigeration system. Today's session we will see the practical vapor absorption refrigeration system. So whenever we are using it in a practical condition, so what are the additional components are added to that, like just like a safety devices to work it properly without any interruption. So it is a practical vapor absorption refrigeration system. In continuation we will see some refrigerant absorbent some properties, and the refrigerant we have seen in the last classes, refrigerants and absorbents. Mostly we are using ammonia and water. Okay, so keep it aside. We focus on this practical vapor absorption refrigeration system. The same functioning, the same the refrigeration effect, how it is getting, all the things we know already. Additional components we have to discuss more in this video lesson. Okay, so let us just recall all the topic what you have learned in the last class, that is working, and we have seen the line diagram of simple vapor absorption system. Hope you have understood in the previous video session. We have seen some video also regarding that, just like a practically how the system is established, and how it is getting the cooling effect. All the demonstration you have seen in that video. And so today you will be able to learn, at the end of this video class you will able to understood the line diagram of practical vapor absorption refrigeration system, and the working principle of practical vapor absorption system. And in continuation we will see the properties of ideal refrigerant, ideal absorbents, and desirable properties of the combination of the pairs, refrigerant and absorbent pairs. Why it is named as ideal means it will not exist, just like a lot of properties will be present in this particular refrigerant or in the particular absorbent. So all the properties will not get in a single refrigerant. Okay, we will see that, right? So coming to the, just we will see some few points regarding that. Why, what is the need when compared with the ideal VAR system? What is the need to learn about this practical vapor absorption refrigeration system? Why? Because additional components which are added to that give us just act like a safety devices. In result, what happens? It will be more efficient and economical, reducing the economy of that particular like a running cost of that equipment. So it may be reduced, and it will work more efficient compared with the ideal vapor absorption refrigeration system. So in addition we will see what are the components added to this refrigeration system. So that is this is the components: analyzer, and the second one is rectifier, and the heat exchangers. So mostly you can establish where the heat exchange, there is a chance to get heat exchange in between the two components. Whenever there is a chance to exchange the heat from cold medium to hot, hot to cold, whenever there is a circuit, so when there is a need of a heat exchange, we can establish the heat exchangers there. So most possible way here in this practical vapor absorption refrigeration system, we are using heat exchanger 1 and heat exchanger 2, in addition with the components analyzer and rectifier. So we will discuss about these three components additionally, what is the need of that particularly, and how they are more efficient and more economical by using these additional equipments to the ideal vapor absorption system. And it can be used for a, if you use these components additionally, so it can be helpful to run it practically. So it is a practical vapor absorption refrigeration system, right? So just have a look regarding this line diagram of practical vapor absorption refrigeration system. So you can draw this diagram. So if you observe, the components other than the whatever the additional components I have told in the last we have seen last slide. If you observe the ideal practical vapor absorption system, so what are the components in that? They are absorber is there, generator is there, condenser is there, and receiver is there, expansion valve is there, evaporator is there, and in between the generator and absorber there is a pump and a pressure reducing valve. So we have seen this case for the ideal vapor absorption system. Whereas for if you observe it practically, look at the diagram, line diagram, what are the additional components and where they are placed. If you observe at the left side of that part, you can see the components placed here. So we'll see the first one, that is analyzer here. What you have seen, the first component is analyzer. So analyzer is placed at the top of a generator. We will see what is the working, what is the use of that particular analyzer component. So analyzer is fixed at the top of a generator part, where you can see all the three connections are moving or coming to the analyzer component. In previous ideal vapor absorption system, all the three connections are connected to the generator, whereas here it is connected to the analyzer part. We will see detailedly the diagram of analyzer, line diagram of analyzer, and the working principle of this analyzer. And next additional component is the rectifier. See, rectifier is placed in between the analyzer and condenser. So after the condenser, if you observe, there is a rectifier or dehydrator. Why the name is given like that, we will see in this, and we will see the clear diagram of a rectifier. This is additional component. And next I have told that two heat exchangers are used in this practical side. That is, if you observe the left, in between the generator and absorber, you can see a heat exchanger is placed. The circuit which is coming from the absorber through the pump, it is make connection. This connection or this pipeline is moving through the heat exchanger and connected to a generator or to the analyzer. And another circuit, if you observe, from the generator where the weak solution circuit is there, so that circuit is make contact with the other pipeline at this side. Okay. And below that you can see pressure reducing valve, and it is make connection with the absorber. If you see the second heat exchanger here, so it is placed in between the receiver and the evaporator component. So you can see here, from the receiver a circuit line is coming, a pipeline is coming here. That circuit is entered into here, and next it enters into the expansion valve. If other circuit you can see, after the evaporation, the line, if you have the pipeline, other pipeline is moving from evaporator to the absorber component. So after the evaporator, the pipeline is entered at this side, and next it enters into the absorber. So here there is a the heat exchange possibility in between this from receiver to expansion valve line, and from evaporator line to the absorber line. Heat exchange will take place. We will discuss it how, what type of heat is getting exchanged here, what is the importance of these heat exchangers, what is the importance of the analyzer, what is the importance of the rectifier, and how it will be more efficient than the ideal vapor absorption refrigeration system. So look at the diagram, line diagram, very carefully. Okay. So this is a line diagram. Now we will focus on the process, what is happening in the practical vapor absorption system. Right. So let us just have a look again regarding the components. So those are the additional absorber, pump, analyzer, rectifier, heat exchanger. Right. So all these are the components, already you know well about that. Next, some fluids used here. Mostly, if you observe, there are in the last ideal vapor absorption system, fluid is used ammonia and ammonia and water. So here ammonia is acting like a refrigerant, water is acting like an absorbent. Mostly used fluid is this combination of these pair, ammonia and water. And here I focus on the working principle again, so you can clearly understood about this functioning of these additional components. So in the generator, the strong solution of ammonia is heated by external source. Means the strong solution of ammonia, what we have discussed earlier, that in the generator there is a heating coil is provided here, so it gets heated, and whatever the solution is present here, that ammonia solution, strong ammonia solution, it get, due to addition of a little heat, it get vaporized. So here the heating coils are the external source. Whenever little amount is heat is added, that strong solution of ammonia, which is in the form of liquid, the vapor ammonia get vaporized. In water, more quantity of water is present in the generator component. So high pressure and high temperature ammonia vapor, what happens here, the high temperature, high pressure and high temperature ammonia vapor, that it will be sent into the rectifier component, or it will send into the analyzer component. So here hot vapors of ammonia, while flowing upwards, vapor containing moisture gets dehydrated and dropped into the generator. So how it is possible in this case means, here during its evaporation, a little amount of water vapor content is present in the ammonia. Ammonia vapors are there, a little amount of moisture. It means combination of the water droplets will be there in the ammonia vapor whenever it is moving into the condenser component. So when we place the analyzer, what will happen? There is a buffel plate type of arrangements will be there. So whenever it is moving upwards, it will make contact with the plates, and the droplets will be break at that point, and only pure ammonia will be sent to the top of the analyzer. And other additional thing what happens here, the solution which is coming out through this left side strong pump, through this pump here, you can see a little low heat for strong solution ammonia is coming through this left side of a circuit, which is entering at the top, at the side of an analyzer at the left side. So whenever it is making contact with the hot temperature ammonia vapor, so little drop in the temperature will take place, and what happens, due to little drop, that moisture will get condensed or dehydrated, and it will get drop into the generator again. So that is the use of analyzer. The dehydrated ammonia vapors enter into the rectifier here. There is next you see the circuit that is entering at the top, at the side of a rectifier. A rectifier is, or dehydrator, it is also a simple case. If you observe, there just like acts like a heat exchanger. So further, the remaining water particles, are remaining whatever the water vapor which is there, which is present in ammonia vapor, it further get condensed in the rectifier or dehydrated. The completely it will get dehydrated in the rectifier. So whenever cooling water is circulated here, so the water particles will get condensed and water droplets will fall here. So through the drip, you can see a circuit is there. Through this drip line, it will again come back to the analyzer component, and it will falls in the generator. So here you can read the point, the dehydrated ammonia vapors enter into rectifier, in which remaining water particles will be separated. Right. So ammonia vapor enters into the condenser. So ammonia vapor is there here, it will get enters into the condenser. Only pure ammonia vapor enters into the condenser. So what happens here, in the first stage, the analyzer is dehydrating the water, or removing the moisture content from the ammonia vapor. Second stage of removing of water vapor, or the moisture content in the ammonia vapor is removed in the rectifier. That is the second stage. So finally, the pure ammonia vapor, it will enters into the condenser component. Now the question arises here: what happens if the moisture content is present or some water droplets are present in the ammonia vapor if it directly sends into the condenser component? So further, what is the problem arising in these components, that is in the condenser or in the expansion wall? What happens here? See, due to low temperatures created here, for example, if you take at the expansion wall, a few low temperatures are created in the expansion wall. Due to that creation, whatever the moisture, little amount of moisture content is there in the ammonia vapor, in the ammonia, it will get freezes, and it will chokes the pipeline here. The expansion wall, what is there here, it will get choked here, and it will stops the passage to flow the vapor, the liquid ammonia into the next components, that is to the evaporator. So that is a chance of getting stuck here or getting choked the pipeline. Due to less temperatures, the moisture may get freezes here. So in the condenser, coming to the condenser component, already discussed, ammonia vapor gets condensed by rejecting its heat to the surrounding cooling medium. So heat rejection is taking place in the condenser component. Now the liquid phase change is taking place in the condenser. Liquid ammonia enters the expansion wall through the heat exchanger. So before this, we will see, before entering into the heat exchanger, what is happening here. The phase change is taking place in the condenser by maintaining the same pressures, and it enters into the receiver. According to the load in the evaporator, the receiver will sense the refrigerant through this through the receiver tank. Now the liquid ammonia enters the expansion wall through the heat exchanger. We will see what happening in the heat exchanger component. Okay, so before the expansion, we will see this circuit. It is entering into the expansion, heat exchanger. So we will look what happened after the evaporation. Again, other circuit is making contact with the heat exchanger. So at that point, we will discuss what is happening. Now simply you have to tell that from the condenser, the liquid ammonia coming with that liquid ammonia is coming from the condenser, entering into the expansion wall. So you know very well regarding this expansion wall. Expansion takes place in this place, in the expansion wall. Due to expansion, low pressure liquid ammonia enters the evaporator. Low pressure liquid ammonia enters into the evaporator component. So it means, due to creation of very low pressures, so low temperatures are created here. Now after the expansion wall, the liquid ammonia, it will enters into the evaporator. Well, regarding this evaporator, evaporation process will take place here by by absorbing the latent heat by the particular refrigerant, that is ammonia. So ammonia changes its phase from liquid ammonia to the vapor ammonia by absorbing the heat from the products and converted again into the vapor state. So here the low temperatures ammonia vapor, which is coming from the evaporator, so it is moving into the next circuit of a heat exchanger. If you observe, it is at the left side from the evaporator. Now low temperature vapor is moving in one circuit in the heat exchanger. If you see other side of the heat exchanger, high temperature condenser, high temperature refrigerant, liquid refrigerant of ammonia is passing through the other circuit. So due to low and high temperatures here, heat exchange will take place. So what is the benefit here? At the right side of the, you see, during entry into the expansion wall, what is happening here? Due to creation of low pressures, low temperatures are created. What we are doing in this circuit after the receiver, we are creating the low pressures, low temperatures when it is passing through the heat exchanger by rejecting its heat to the other circuit of the heat exchanger. Heat exchange is taking place. At one side, it is temperature is reduced, and other side of the circuit, temperature of the vapor is increased. Okay. Next, that it enters into the absorber component. So low pressure refrigerant will enters into the absorber component. Now see the next case. So So the products are cooled in the evaporator at a low pressure. Vapor refrigerant from evaporator enters into the absorber. So in the absorber, what happens? Ammonia is absorbed by the water and ammonia is dissolved in the water. So completely it will get dissolved in the absorber component. Due to low pressures are maintained in the absorber, so it will receive the whatever the refrigerant is coming, that will enters into the absorber. So already some weak solution is present in the absorber. It means the combination of ammonia plus more quantity of water is there. So after entering the vapor ammonia, from the evaporator, it will mixes with the water and prepares the strong solution in that. So to reduce, due to addition of that, further temperature is increased in that. So to reduce that, we are providing some cooling water circuit there to reduce the temperatures. Right. So this strong solution in the, again the question arises, already in this heat exchanger we are heating at this side. That heat, that little amount of heat is added to the refrigerant and it is entering into the absorber. What happens here, the problem is, if the temperature is more, the more the temperature is there, the whatever the pressures inbuilt in the in the solution is more here. So due to the differences in the pressure, so there is a chance of a uh, there is a chance, less chance to avoid the entry of the vapor refrigerant coming out from the evaporator into the absorber. So I hope you have understood that. Must and should low temperatures has to be created here, then low pressures can be maintained in the absorber. Okay, so then only the refrigerant will enters into the absorber from the evaporator. Here the strong solution of ammonia which is present in the absorber, with the help of a pump, it will be pumped to the analyzer component at the top. So here again the heat exchange is taking place. Here the low temperature, further addition of heat is taking place. At the left side you can see, after the pumping it will enter through the circuit in the heat exchanger. That weak solution which is coming from the generator has high temperature, so primarily it is heating in the heat exchanger before heating in the generator. What happens, the cost of the equipment will get reduces, the functioning of that, more efficiently it will get work. So cost of the heating in the generator reduces, the cost of the cooling in the evaporator get decreases, in the absorber, sorry, in the absorber it get reduces. So it's pumped, thus the cycle is repeated again and again. Okay, so we will clearly see the functioning of this analyzer, rectifier and heat exchanger one by one. Hope you understood the cycle. It's very easy and very important. Right, we will see the first, the function of analyzer. So where it has placed, analyzer is placed on the above of the generator, right? And here the we'll see the line diagram. The first we'll see the function of analyzer. What happens when ammonia is vaporized in the generator, some water is also vaporized. As I earlier discussed, a small quantity of water is also getting vaporized. So this will flow into the condenser along with the ammonia vapors. What happens here, it is flowing into the condenser along with the ammonia vapors. If you are not placing any analyzer or rectifier there, what happens, if these unwanted water particles are not removed before the condenser, they will enter into the expansion valve and gets freezed and choke the pipeline, as earlier already discussed this thing. So must and should analyzer has to place before these components, so it will act like a safety device. Now, so analyzer removes these unwanted water particles before the it entering into the condenser component. So analyzer has to place before the condenser part. It means above the generator component, right? Next, this is the diagram. You can see here what we are doing in the generator. At the bottom you can see is the primary component. We are using the heating coil inside that. So whatever the solution is there, so it is getting heated with the help of heating coil in the generator. So a vertical column which is provided on the top, you can see it is a plate type of structure, a bevel plates. So a side by side arrangement is placed the alternate arrangements of plates can be placed here. Now, so here there is the right side you can see there is a connection to a rectifier. It moves, the vapor will move, ammonia vapor will move to the rectifier, and you see at the left side the strong aqua ammonia solution which is coming from the absorber component will enters into the generator. So during here whatever the vapors created here due to heating, that it will first the water vapor makes contact with these plates, the buffel plates, and will, and also it will make contact with the temperature which is having low temperatures of the strong ammonia solution. So due to that the fine water particles will get droplet and falls down here. Now we'll see the working of analyzer. So the strong solution from the absorber, the strong solution from the absorber enters into the generator from the top of analyzer. As earlier discussed, it comes downwards over the trace and comes in contact with the ammonia vapor and gets cooled. So it means now here uh, the strong solution come downwards over the trace and comes in contact with the ammonia vapor and gets cooled. So during this process the water vapor is condensed due to heat exchange. Here the water vapor condenses and water gets accumulated at the bottom. Again the water droplets will fall at the bottom. So the dehydrated ammonia means the complete removal of maximum level of removal of water vapor will take place here in the analyzer, and the dehydrated ammonia vapor flows into the rectifier here through the other connection here. Now we will see the continuation if it next enters into the rectifier. So this is the final stage of elimination of a water particles in the rectifier. So it is placed after the analyzer but before the condenser component. So further elimination of water vapor particles are done in this. So rectifier eliminates any water particles present in ammonia vapor leaving the analyzer. This is the final or second stage of the removal of water vapor particles. So here again the same thing, a vertical column at the bottom you can see there, and here you can see a cooling coil is provided in this, and deflegmator where you can accumulate all the vapor in this at the top of a rectifier. So here from analyzer it is entering through this rectifying column. It means it making again the same process, it is making contact with these buffel plates, and due to further cooling process whatever the water vapor is there present in the ammonia vapor, it will further get condensed and further drop at the bottom. Again that water particles are again sent back to the generator component. So this is a diagram, you can note it down for a rectifier. And at the other side at the top you can observe this pure ammonia is sent to the condenser component. Okay, pure ammonia sent to the condenser component. This is how we are making more efficient to work. Okay, right, and next we will see the function of rectifier. Yes, so it's a vertical column and a deflegmator. Vertical rectifying column contains baffle plates. Baffles are there, just like this vertical, this horizontal plates which are provided in the vertical column. You can see it side by side they are placed. They are baffles. And here already explained the deflegmator accommodates external supply of cool water. So here just it will give the space to that in the deflegmator where the cooling coil circuit is provided here. The further condensation of water will take place which is present in the ammonia vapor. So partially dehydrated ammonia vapors enters the rectifying column from the analyzer. So it means finally this vapor flows from over the baffles and come in indirect contact with the circulating cold water coils. So moisture gets condensed and drips down to generator via rectifier. Again it will get dripped down to generator. Again it will, that water particles sent to the generator via rectifier. Other port is provided here. So dry ammonia vapor so leaves the rectifier and falls into the condenser. So this is regarding the rectifier, function of a rectifier and function of an analyzer. Next we will see the heat exchangers. So first we see the which is located between the generator and absorber. In between the generator and absorber, the strong solution at low temperature is pumping from the absorber, and the absorber is at the bottom position, where you are from the absorber the strong solution is pumping to the generator component with the help of a pump. So the strong solution is at low temperatures. You can see at the left side of a circuit here. Okay, next that hot weak solution is returned back from the generator. Whatever the weak solution is there, more the quantity of water and less quantity of ammonia is present in that. So that hot weak solution is returned back from the generator to the absorber component. So here this is a hot, right side of a circuit is hot weak solution, left side of a circuit is at low temperature. So due to this low temperature and high temperature circuits, heat exchange will take place. The strong solution is heated, and at this side the weak solution, it has to get cooled in the analyzer. That is done primarily in the heat exchanger. So primary function of heating and cooling is taking place here due to the heat exchanger. So that is the advantage here. Now both solutions will pass through the heat exchanger. Heat exchange takes place between the two fluids. The strong solution is heated and weak solution gets cooled. So this is what we have explained regarding this, the heat exchanger, right? So if you see the advantages, what happens if you like that heat exchange take place, so it will reduces the cost of heating in the generator, right? Very good. What's happening, primarily it is getting heated. So what happens, cost of heating, more the time we cannot heat, more the time the heating coils cannot be used. So further if it is the time is reduced, the cost of heating in the generator will also reduces. The cost of cooling in the absorber, we see in the absorber there is a cooling circuit. So you have to cool the whatever the hot weak solution which is present in the absorber. So cost of cooling can also be reduced. So that is done primarily in the heat exchanger. And overall what happens, overall it will falls on the overall efficiency. It means improves the overall efficiency of the system. And here, so this is regarding the practical vapor absorption refrigeration system. Hope you have understood all the additional components, what is the use of that, how it is increasing the overall efficiency, and how it is more economical than the ideal vapor absorption refrigeration system. And let us focus on the next topic, that is desirable properties of ideal refrigerant. Please. So here these are a few points. It should have high critical temperature and pressure. So ideal refrigerant you are taking, for example ammonia is like that. So take the example, should have high critical temperature and pressure. So high enthalpy of vaporization, low specific heat. So I'm not explaining these properties because already we know all these things. So just note it down, the points or the properties of the, what are the properties has to be present in the ideal refrigerant. Okay, like low specific heat, low molecular weight, and chemical stability should be there. Like next, high affinity for absorber at low temperatures, less affinity for absorber at high temperatures. It means if you observe clearly, a combination of refrigerant and absorbent is there. The affinity should be high at low temperatures. It should maintain very high affinity, combination of refrigerant and absorbent. Whenever less affinity means if addition of heat, it means whenever it reaching to some temperatures, high temperatures, increasing the temperatures, so they may get separated. like ammonia and water is getting separated when we adding some heat to that, so it should be less affinity. It should not get more affinity. Why? Because we have to add more and more heat. If I add a little amount of heat, the affinity it has to less, then the both can be separated very easily. That should be present in the ideal refrigerant. So should have vapor pressure characteristics so as to boil at minus 45 degrees centigrade to 2 degrees centigrade and condense at 40 degrees centigrade. So they are very feasible if you use these temperature uh, levels, like, condensation take at 40 degrees centigrade atmospheric pressure. Next, if you take absorbent, like just like example of water, so it has properties. It should remain in liquid state under operating conditions. They should not get vaporized. Why? Because ammonia with a little addition of amount of heat, it is changing its state to the vapor form. So in the at that particular temperature, the absorbent should remain at a liquid state only. It should not get vaporized state along with the ammonia or along with the refrigerant. If both they get vaporized, there is a no need of there is a useless of this refrigerant and absorbent pair. Absorbent must and should remain liquid state under operating conditions, and greater affinity for the refrigerant. So it should well mix with the refrigerant. It should have greater affinity at low temperatures, and it should mix with the refrigerant, and it must and should have high boiling point. As earlier discussed, must and should have high boiling point compared with the refrigerant, and it should have low specific heat. It's also important point. And same, the chemical stability should be there and the thermal stability should be there. It should not attract to the it means whenever low temperatures are there, it should, if it should vaporizes, it is a waste. So it should have some stability. The property of that particular, it should be standardized one. For example, water at 100 degrees centigrade, it will get disturbed. It means it will changes its phase. So up to that, below the temperatures, it will maintain some thermal stability. Like it should chemically it should be stable. Whenever it mixes with some like refrigerant having some chemical nature, whenever it mixes with that, it should maintain some stability. Low viscosity should be there, and low viscosity, if it low viscosity, right. Heat emitted should be minimum when refrigerant is absorbed by the absorbent. It is also important point. And low molecular weight, it is also one important point. And combination of the pair, you can see the same things again. It should have low specific heat, and so that small amount of heat, temperature of mixture can be increased easily. Next, low freezing point. Both should not form solid phase. When they mix together, should not form the solid phase. Both should maintain low freezing point, should have low specific heat. So all these points you can note it down. They are very important properties when they are forming like a pair. And it's also very important, it should not be non-toxic. If they are toxic, you know what will happen. And non-flammable also. At particular temperature, it should not get flammable. It should not be burst. It means no heat, no the flame should be added to that whenever some heat is gained by that particular pair, refrigerant absorbent pair. And both should be chemically stable at all operating conditions. If you combine the refrigerant and absorbent properties, desirable properties, so you can notice all these properties of the combination of the pairs, refrigerant and absorbent pairs. So these are few properties, very helpful, and you should remember. Few other additional points. Low viscosity should be there. Why? Because it should be pumped with the help, the pump work will be there. So with the help of a pump, you have to pump that liquid to the different components. So must and it should maintain the low viscosity. If there is high viscosity, the different special case of pumps should be used, where the cost of the overall equipment will get increases. And combination of these two will not affect any the pipeline material. It should not cause any corrosion, right? So absorbent should have high solubility at conditions in the absorber. So absorbent should have high solubility. Next, pair should have low solubility at conditions in the generator. Next, you can see these are the refrigerant absorbent pairs. If you see the state of absorbent, what happens when they are absorbent mixes. So here they both the absorbent is in the liquid form, that is ammonia, water. They will seen in the liquid form. The state of absorbent of sodium thiocyanate is solid form. So mixing of ammonia and sodium thiocyanate will act like a pair also, a refrigerant absorbent pair. And other one is also here the absorbent state is a solid. It means calcium chloride is in the solid form. So mixing we can use along with the combination of ammonia. Like a other state of absorbent is a solid, there it is lithium nitrate is absorbent, which is in the solid form. So we can make mix with the ammonia. And as in the previous video lesson I have told that water and lithium bromide, here water is will act like a refrigerant, lithium bromide acts like an absorbent. And what is the state of absorbent here is solid. Now water will circulate in the system by giving the refrigerating effect in the system. So it is a different opposite case here. And lithium chloride, if you observe, most of the absorbent states are in the solid form only, lithium chloride. And water will act like a refrigerant here. Next one is the refrigerant methyl chloride, and absorbent is dimethyl ether, and the absorbent state is a liquid state. So then note it down, all these are pairs. Most used pair is a ammonia and water, and next one is the water as a refrigerant, lithium bromide as a absorbent. So these two are most frequently used cases. Mostly they are using industry purposes. So generally ammonia water combination is used in vapor absorption systems. So we'll see what are the advantages of using this pair always. Ammonia is highly soluble in water. It have greater affinity at lower temperatures. It will mix well with the water. So 1 cubic meter of water absorbs 800 cubic meters of ammonia. So you can see the volume here. 1 cubic meter of water absorbs 800 cubic meters of ammonia. It has very greater solubility in the water. So why you are using this combination water and ammonia? Latent heat of ammonia is 1313 kilojoules per kg at minus 15 degrees centigrade. So it is also one factor why you are using this combination. And critical temperature of ammonia, if you observe, it is 133 degrees centigrade. So it should have refrigerant property. It should have high critical temperature. So it is very high critical temperature, 133 degrees centigrade. So we can use ammonia as a refrigerant. Specific heat of ammonia is 1.12. Boiling point at atmospheric pressure is minus 33 degrees centigrade. Boiling point. Okay. So disadvantage of using this pair is combination generate more heat in absorber. So cooling arrangement is needed. Combination generate more heat in the absorber. So cooling arrangement is needed. So what happens in the absorber? There is a circuit placed where cooling water circuit is provided there. The combination generate more heat, use of ammonia and water. So must and should cooling arrangement is provided there. Since corrosive mixture, special material should be used. Okay. So there is a one disadvantage. Combination of these will give some little amount of corrosive nature. So special material for the pipes should be used. Okay. So this is regarding the desirable properties. If you observe, hope you have understood all these classes. It's a line diagram of practical vapor absorption system, working principle of practical vapor absorption system. We have seen the working of analyzer, rectifier and heat exchanger, and desirable properties of ideal refrigerants, properties of absorbents, and properties of combination of the pairs, refrigerant and absorbent pairs, and commonly used refrigerant absorbent paints. We have seen mostly used. We have listed out all the pairs one by one, and seen the importance of ammonia and water mixing together.